So my capstone is gonna be on analysis and comparative performance of open source intrusion detection. So what I did for my work was I compared open source intrusion detection system, their performance and differences, and I chose three commonly used IDEs, which are Suricata, Snort, and Bro. So to find out their performances differences, I set up experiments and I got results for those experiments, which we would go over on subsequent slides. So my literature review pretty much covers the existing researches, theories, and evidence of my work. So the literature review gave me like an in-depth understanding and insight into like the work, different works that have been done on IDSs, and also researches that have been done on this topic, which pretty much helped me to understand and also come up with a good work. So my method for my experiment, I set up test bed that compares Suricata, Snot, and Bro. I also analyzed every situation of my test based on the processing conducted on the packet. So for this experiment, I want to point out that Suricata and Snot ideas are put together and compared to Bro. I also examine drop packets based on default setting for these three IDSs, which are Suricata, Snot, and Bro. So for my experiment, I did three different experiments. The first one was the default OS and IDS configuration. The next experiment was that I did is I replaced a network socket packet to capture modules to enhance capturing performance. And the third I did was optimizing IDS configuration. So for the default OS and IDS configuration, I only captured vital changes. I conducted the experiment based on the transmission speed defined by the TC preplay software. TC preplay max speed can be shown using MBPS. So for this experiment, the software has to match the speeds and cannot exceed the maximum speed. So after the experiment was conducted, for the results for the default OS and IDS configuration, this this figure here shows Suricata, Snot, IDS setup and compared to Bro. So looking at the figure, you see like the three IDs I chose, which are Suricata, Snot, and Bro in their default configurations. The result here tells you that there was a drastic change, with a Snot dropping the highest when the speed got higher and Bro followed while Suricata attained the best outcome. So with higher speed, pretty much Snot, dropped the highest. Bro was the second, when Suricata was so far has like, the best result. For this figure here shows a CPU utilization for the three IDS. Now, so you see the percentage of CPU used by Suricata, Snot, and Bro in their default configuration. So from the figure, you could see that Suricata used more processing power compared to both Snot and Bro. So on the second experiment, I realized in the first experiment that the default configuration for Suricata, Snot, and Bro was not the best for higher speed traffic network analysis that goes beyond 100 megabits per second. So what I decided to do was to alter the LDS configuration to see if I would get like a better outcome or a better result. So I did alter them to find a better result. For Snort configuration, the first thing I did was I adjusted the default memory limit from 8 MIB to 512 MIB. Now, the reason why I did this was to prevent warning messages for memory cap exceeded. I also set up the number of concurrent sections to track to 1048575. This is pretty much the max for Snort. This max Snort can support. So regarding the HTTP traffic, Snort default configuration had no limit set for the HTTP traffic analysis, which in turn heavily loaded the CPU for higher volumes of HTTP transfers for both server flow and client flow depth. So Snort manual pretty much shows that Snort default values for client flow and server flow depths are 300 bytes. This basically tells me that Snort IDS can only inspect the first 300 byte server response and client quest packet. But for this experiment, my goal was to ensure optimal intrusion detection without emission, right? So what I did is I increased uh, the flow the flow depth to 1460, and this is the maximum for Snort. So after I did all this, the outcome was pretty good. I had 25% fewer drop packets, generated. So this was pretty much a good outcome. So for Suricata, I also adjusted the default memory from 32 MIB to 512 MIB. So just like Snot, after like I did the adjustment, the reason I did this adjustment was me wanting to like make sure like no session was cut off or trimmed off due to like low memory. So for me to be able to like make sure all through my texting cycles, I don't have no, you know, trimmed off section for low memory. I had to like, adjust the memory. But after the memory was adjusted, there was no further improvement. So it didn't really matter much. So this next slide shows a table. This table shows the drop packet for Suricata and Snot after optimizations. So according to the table, we see that Snot needs more improvement after optimization. The graph here is a representation of the table that I just showed. So this graph is a graph of a drop packet for Suricata and Snot after optimization. Now looking at the graph, you see the difference between these two ideas. Snot requires improvement while Suricata displays a perfect relation. So the next slide is the CPU utilization for Suricata and Snot after optimization. So Snot CPU usage remained constant, and the reason why it remained constant is because I used just one processor. For Suricata, it showed 30% lower CPU usage after optimization. I applied the CPU affinity to limit Suricata to using only 4 processors. Otherwise, the value could have been higher. And the reason why like I limited Suricata to only 4 processor was was me trying to like shy away from hyper-threading. So I felt like to prevent hyper-threading, if I limit the processor to just 4, it would prevent that. So on my third experiment, I modified the network socket capture modules to increase performance. So I was able to do this by increasing the lip cap buffer sizes. So the lip cap default size is 34 KIB. So what I did is I adjusted the buffer size to a higher value. So we all know that Linux has a max buffer size of 2 GB, but the TC preplay system still have like had like memory left. So memory itself was never an issue for this experiment. So for the configuration, I achieved between 5% and 15% fewer drop packets for Snort than in the previous experiment. The outcome was not stable. So what I had to do is, to get like, a better, accurate result, I had to like do the experiment over and over again. And this was my way of getting, accuracy. Also, when you look on the next slide, would explain better. Now, this next slide is like a table, right? This table shows the drop packets, you know, the drop packets using the 2 GB lip cap buffer size and the previous configuration. So this graph explains it better, right? Looking at the graph, you see like the drop packets using the 2 GB lip cap buffer size and previous configuration. So looking at it, you could see like Snot analyzed 420 megabits second traffic minus any drop packet, which pretty much shows great improvement compared to like the other experiments. So also you could see like the maximum transmission speed is higher for SNAT here, and this you could tell by looking at like the peak curve. The peak curve shows you that the maximum transmission speed is much higher here. As for Suricata, you could see Suricata achieved a zero dropped packet. So in conclusion, my work pretty much analyzed and compared the performance of these three commonly used IDEs, which are Snot, Suricata, and Bro. These ideas are used, for their accuracy in catching harmful and malicious traffic in our networks. As we know, like cyber attacks continues and will not stop. It's left for users to develop ways of preventing or fighting against these attacks. And also, it's paramount to understand that choosing the right ideas for your network will help in your fight against this cyber or malicious attacks on your network. So my study pretty much help users to see for themselves the features and performance levels of these commonly used ideas that I've addressed. And by seeing, going through this information, they can make their own informed decision of the one that will work best for them or the one that will be best for what they do. The next two slides covers my references, and this pretty much ends my presentation.